Hello and welcome back to High Peak Education. I would like to record another video where this time we are looking at an electromagnetic induction problem that has the area changing as a function of time. So this is a bar on rails. Let's let these rails be frictionless, and we're going to use the data that we're given to calculate some things. So we use the data given in the figure below to find the motional EMF. Let the length of the bar be 10 centimeters. B, what is the current? C, what is the direction of the magnetic force on the rail? Okay, so let's label everything with the appropriate units and the appropriate symbols. So let's start off here, since I have the black pen out. 2.0 ohms, I think that's the resistance. So let's call that capital R. Let's also label the velocity. That's going to be here in green. I think this is the V equals 0.50 meters per second. And then these are going to be magnetic field vectors. So each of these is a magnetic field vector, and I think that the magnitude of the magnetic field is into the page, and it's equal to half a Tesla. All right, and we also know that the length of the bar, that's this length here, the part that's sliding along the rails, is 10 centimeters. So L, if converted to SI units, should be 0.10 meters. All right, so let's first calculate the motional EMF. So the motional EMF, recall, for part A, should be given just by BLV. So B is the magnetic field magnitude, L is the length of the bar, and then V is the speed. Okay, so I think that's how we can calculate. So let's in fact go ahead and calculate. So B, the magnetic field magnitude, was half a Tesla. All right. Then we have to multiply that by the length of the bar, which was 0.1 meters, and then we have to multiply that by the velocity, that is the speed of this bar, and that's 0.50 meters per second. All right, so let's get this motional EMF, and let's say that, okay, this is half times half, that's 0.25 times a tenth. So that's 0.025, and that's going to be units of volts. There is our motional EMF. Let's look at part B. Part B, what is the current? Well, if we have the motional EMF and we're looking for the current, we can take the motional EMF and divide by the resistance, because we can just use Ohm's law. So that's 0.025 volts divided by the resistance of 2.0 ohms. Okay, and then if you calculate this, we're just dividing by 2, so we're taking half. So that's 0.0125 amperes. Notice that would be 12.5 milliamperes. This is sort of a somewhat typical value. And lastly, part C, it says, what is the direction of the magnetic force on the rail? So let's label that in a separate color. So we want to know what's the direction of the magnetic force on the rail. So let's first determine the direction of the electric current. So the electric current is always going to be in a direction to resist the change with respect to the changing magnetic flux. So notice the area of this circuit is getting smaller. So since the area of this circuit is getting smaller, then the magnetic flux wants to reinforce this area. How do I know that? Because if it's getting smaller, resist the change means make this magnetic field that goes out of the page stronger. So the thumb would point out of the page by right-hand rule 2, and the fingers would rotate like so, which is counterclockwise as viewed from above. So the direction of the electric current would be counterclockwise. So this is the electric current. And let's think about what the direction of electric current is. So it's down in this bar. So that's the direction of I times L vector. And we cross product that with B, which is out of the page. So the magnetic force is going to be to the left. So we'll get that this magnetic force is to the left. And notice these magnetic forces with these moving bar problems are going to tend to be in the opposite direction of the velocity. They're going to tend to slow these bars down. You can imagine if we had a push force in this direction to the right, there would also be a responding force, that is a Newton's third law force, which kind of, pulls us back to the left. So that's kind of the basic idea. Or at least we build up to that force, so to say. So it's going to be to the left, that is in the negative x direction. That is, if we call the positive x direction to the right, which is fairly traditional. All right, so that ends this problem. Thank you all very much for your attention. Thank you for watching High Peak Education. Please smash that like button if you enjoyed this content, and please share this video amongst your social network. Please subscribe to the channel to grow the channel, and I will see you in the next video.